So last time we were analyzing the partitioning estimator, and okay, so the idea was to write this quantity of interest, which we sort of convinced ourselves it's a good thing to look at. It's a form of conditional MSE, condition on the training X's. And so we're trying to see how close the regression function is to the true regression function. And we argued that this can be done in two steps, basically, because it's the MSE. It has this decomposition in terms of the bias squared plus variance. And then we focused on, so this is called the bias variance decomposition, or bias variance trade-off. It's not a trade-off, but when you try to use this to optimize the this equation. When you try to optimize or use this to optimize the estimator, it's called bias variance trade-off. And the idea was, as we wanted to compute this for the partitioning estimator, and we so introduced some notation. So there's this empirical distribution or empirical measure. This is the empirical distribution of the X's. And by the law of large number, we mentioned, or like argued, that this converges to the true distribution, which is this probability measure or probability distribution. The probability that X belongs to any set is given by, basically, it's the definition of the distribution. Distribution is a set function assigned to every set, this probability. And so we wrote down the partitioning estimator like this. So it's a weighted average of yi's at these particular weights. And we went on to calculate the variance. So the variance was under the assumption that the variance of y given X is constant. So this is an assumption that we make. We could drop that, but for simplicity. So under that assumption, it ends up being the variance ends up being this, the sigma squared over n, this empirical distribution applied to the cell of the partition that contains X, and that's approximately, again, sigma squared n times this measure of the set under the actual distribution. So by the law of large numbers, this happens. And so if we looked at the case where you just have 0 to 1, if we mean like one-dimensional space and we partition it into interval of length h, then and the distribution is uniform. Then the probability that like a random X lies within one of these intervals is h. So that's the definition. So the mu of AX is going to be h, and so we saw that this is like a good approximation of the variance for large n. As like h, the bandwidth here, h plays the role of the bandwidth. It's not exactly the bandwidth, but as the same interpretation of the bandwidth in the kernel regression or L-Variance regression. So as h goes to 0, then this goes to close to infinity. So it also makes sense when you make h smaller, there are fewer points. So remember, this is basically like fraction of points that lie on land within AX. And so as I make it smaller, there are a smaller number of points that land in there. And so it reduces the capture beta's h. So this is the proportion of the points that land in that cell is h. And so make it sigma squared over n times h. So this blows up. So you want h to be large, capture more points to lower the variance. On the other hand, we analyze the bias, which is a little bit trickier. And we ended up showing that the bias is, or actually the mean, this conditional mean of eta hat is this quantity, which is saying that we average. In general, it's this. So it's a weighted average of eta i's by the weights that are given by this distribution over that cell. Or in the simple case, it's just everything simplifies. So the distribution of the x is uniform, so you're basically integrating eta within that cell and then divide by the length of the cell. So it's like really an average. Think of the if it was discrete, it would be like a sum over a bunch of points divided by how many they are. And this h is basically integral of just 1 bx over ax. Okay, so you're integrating eta over ax divided by the integral 1 over bx. So it's really a weighted average if you think about it. And so what matters is that for any x that is in this partition, so x, like this is the cell of the partition that contains x, but for any other x, this is going to be the mean. Okay, so this is going to be constant for every other point, which is in here, and it will be the average of the eta over that cell. And so effectively on expectation, this partitioning estimator behaves like a piecewise constant. So it's piecewise constant in the sense that it's constant over these cells. And it's not, it's actually true even not in expectation, because of the way you construct it, you always get the same value for eta hat x over a cell of partition. So it's going to be a piecewise constant in general, but the mean is also going to be piecewise constant, and it's going to have some variation around it. So whenever we draw eta hat x, because of the randomness in the y's, these let's say levels shift, but they're centered around this value that we calculate. Okay, so there's some variance. So sometimes it might be like here, sometimes it might be here, sometimes it might be there, but on average, they're there. Okay, and then the variance we calculated. So the variance exactly is what we calculated, sigma squared over. It doesn't depend on h, so you can actually put a confidence around this. Confidence interval. In any case, so that's the, yes.
Why is not happening that here?
The what?
Why is not happening that having multiple?
So I'm plotting the expectation here. Okay. That's what I'm doing. So eta hat x itself would be variable. I'm plotting the expectation. So expectation is assuming that we condition on the training data. This is like the training x's. This is fixed. And so the thing is that even if I had this is not necessarily a good approximation of eta, unless I let the bandwidth for this h go to 0. As I make h go to 0, I get a better approximation. And so you can calculate the error of approximation, which is really the bias, because this is the expectation, and you're comparing the true eta x, so that's really the bias, and the bias squared appears in the MS eta. So this is not going to go to 0 unless h goes to 0, and you can convince yourself this is the result in analysis that as h goes to 0, this converges to the point because the ax is shrinking. So you have, okay, the cell could be like this, and then as I make h smaller, so this shrinks to this point, like, and then this point. So ax is always containing x, but the size is smaller and smaller, and I'm averaging eta over the smaller and smaller portion. Eventually, I'm just averaging over a very tiny neighborhood of x. So this is going to converge to, let's say for simplicity that eta is continuous. Right? So it's a little more general. So convergence to eta x for almost every x. Or let's say if eta is continuous, this is the first truth. Actually. So in order for me to make the bias go to zero, I have to make the h go to zero. We can do a little bit more, so you can find the order of how fast this bus goes to zero if you assume something about the let's say complexity of f. Okay, so intuitively, the decisions think for like people approximation here, you think of functions that are smooth as less complex. So this is smoother. This one is like rougher, like less smooth. And the less smooth it is, the worse this approximation would be. So you have to make h very small. If it's very flat, like smooth is like close to being flat. Because you can measure it actually by the derivative, how fast the derivative changes. So if you have this very smooth curve for eta x, then you hope that this goes to zero faster as h goes to zero versus this. For this, you have to like make it smaller. So the way that people measure it is like with how fast it goes to zero. And so what I'm going to do is like I'm going to mention this condition. So far is it good? Like people are on board. Okay, so what I'm going to do is I'm going to make an assumption here. I want to give you something concrete. So assume, so in order to analyze or like bound the bias further, we need to impose some assumptions on the true regression function. On eta, the true regression function. What I'm going to assume, let us assume that eta is L Lipschitz. So anyone knows what Lipschitz means? Okay, so no one. So this is a very cool assumption then to learn. This is another thing that you can learn in this class. So these are functions whose derivatives don't change much. So an easier way to say is like it's L Lipschitz is if eta of x. If I look at 2 points, I get the absolute value. I take 2 points, like x and y, or maybe not y. That's okay. X prime. 2 different points. Okay, let's do x and y. Okay, let's do x and z. Okay, x and z. I take 2 points. Look at the difference of the function. This is bounded by L times. Let's say in the univariate case, everything on the real line is x minus. It's bounded by how close x and z are. So in the 1D case, it's like that. In the general case, general D-dimensional case, you get L times the norm of x minus c. So this is the L2 norm. Let's say focus on the 1D case for now. So actually you can do it in the general case. It's fine. What it's saying is that if I know how close x and z are, then multiply by a factor L, that's how much the eta can change. So it can't change too much if I'm not far away. Okay. And this you can show there's a theorem, I believe by Rademacher, that functions that look like this effectively are differentiable everywhere, almost everywhere. So then like this is equivalent to saying eta is differentiable almost everywhere. And the derivative is bounded by L for all x. Or in the case of D-dimensional case, the gradient, the norm of the gradient is bounded by L. So the gradient, the derivative is like bounded. Okay, so you can't have like too much. So this is, if you look at this function, for example, this has the derivative is like very moving, varying slowly. This one has a very like sharp derivative, right? So derivative is like the slope of the tangent. So this is going from derivative 0 to a very large, like the absolute value of derivative, but this one is controlled. So by controlling the derivative, you can control the smoothness. And you can go like higher order derivatives, you get higher order notion of smoothness. So controlling the derivative or derivatives of a function is a general way to control its roughness or smoothness, the opposite of smoothness. And smoothness is a good condition to assume about the functions because this controls how well you can approximate them. This is like controls how well. Okay. Yeah.
Sorry, what is L again?
L is like a constant in a unit. So I'm going to say it's L Lipschitz if it holds with this condition. So if it's hold with 2, it's 2 Lipschitz. Hold with 1, it's just a constant.
So does that mean a constant times the
Yeah. A constant times the absolute value. So for example, it could be like 2 times x minus z, then it's 2 Lipschitz. Okay, it's just a constant. Right?
and it's combined outcomes, the data X is with the agent Z.
So it controls how eta values are, how close they are, assuming that how close the inputs are. So if the inputs are close, like by a factor of, so let's do this, for example. So suppose, like example, what's the simplest example in 1D that you can think of? Of a Lipschitz function. No, the simplest is constant. So the constant function definitely. So if like, let's say eta of x is a constant for all c, right? Then eta of x minus eta of z is 0, which is definitely less than anything that you want. So it's like L Lipschitz. So it's L Lipschitz for any L. This is very smooth. The constant function is. But the tricky, like the better one is like eta of x is like alpha x, right? For some alpha, linear. Or actually like affine. So let's say ax plus b for a and b real. Okay, x is also in R. Okay, so this is a linear function or like a affine function. If you plot it, it's like that. Right, so is this Lipschitz? A Lipschitz or Lipschitz with constant. So you can say L Lipschitz or Lipschitz with constant L. So eta of x minus eta of z is going to be what? A times x minus z, right? And so this is exactly a x minus z. So it's definitely less than or equal to x minus z. Equal, so this condition is satisfied, so it's actually the absolute value of a Lipschitz. So eta is a Lipschitz. Usually you would say this with L positive. It has to be positive because it's on the other side. So it could be like -2. -2 and 2 are the same. So this is like the absolute value of the slope. If you believe Rademacher's theorem, tells you another way to characterize it is by controlling, by looking at the absolute value of the derivative. So what is the derivative of this? A. So this is going to be absolute value is A. This is for all A. For all X, so it's really definitely less than or equal to A for all X. So by Rademacher theorem, that's another way of showing that Lipschitz. Yes.
Will one Lipschitz more smoother than two Lipschitz?
Sort of, but so if you want to really like look at it from an approximation perspective, you look at this class. So that constant doesn't really matter as much. So the class of L Lipschitz, because I can always so for example, if you have something which is L Lipschitz, if I divide it by L, then it's going to be 1 Lipschitz. So it's really that a scale is not as important. You can think of it, yes. So for example, if you think of this function is less smooth than this. I wouldn't say that. If you want it, you can say that. But usually you look at this class, the fact that the derivative is bounded is what matters. Okay, so the class of L Lipschitz, you usually don't worry too much about the constant. It comes up, that constant comes up. But this class, for example, versus the class for which the derivative is unbounded. Okay, that's the tricky part. So an example which is not Lipschitz is, can you give me an example which is not Lipschitz? Tan inverse. Yes, okay, so that goes to infinity, true. So tan inverse. What is tan inverse? Like, I think I forgot what tangent looks like. So how does it look like, tangent? This is tangent, right?
Yeah.
So let's not invert it. In itself is like problematic, right? No. Let's do something which is not going to infinity. So, sorry?
Mod X. Modulus of X.
Modulus of X. What does that mean? Oh, this, okay. Is this not Lipschitz? So Rademacher's theorem tell you that it has to be almost everywhere differentiable. So this is almost everywhere differentiable. So except that point. So it's a finite number of points is fine, countable any number. Almost everywhere differentiable derivative is either 1 or -1. So that's what that is bound. There's really 1 Lipschitz. Eta of X is absolute value of X is 1 Lipschitz. A simpler example, like just simple example, this guy is not. X squared is not Lipschitz. Why it's not Lipschitz? If you believe Rademacher, eta of X squared, eta prime of X is 2X, so this is unbounded. It's not Lipschitz over the real line. So not Lipschitz over R, but Lipschitz over, let's say, 0, 1, or like any bounded set. So if I bound the set or a bounded set, derivative is controlled. But not Lipschitz over the real line. Okay. Another example is like this guy, root X. So this one, the derivative goes to 0 at 0 goes to 0. So it goes to infinity. So this is not going to be Lipschitz again on it, like 0. Okay. So it matters, like the domain matters as well. So this guy is sometimes called locally Lipschitz. So any bounded set is Lipschitz X squared, but not over the entire line. So locally Lipschitz, and then like the neighborhood. Some point it is Lipschitz, but not. So if you want, this we don't really need, but you can say locally Lipschitz. This is more problematic. So there it blows up. Sounds good. An example of a good one from like later might be, so the things that people use in neural networks, like sigmoid function. So the sigmoid function, if you look at it, it's 1 over 1 plus e to the negative x. So it gets flatter, and the worst case, the derivative is at 0 is 1/2. That's the largest it can be. So it's a Lipschitz function. Another one is the ReLU, which people use in neural networks. This is again not linear, but Lipschitz. And the tan edge, maybe. That's also very similar to this, similar looking, like tangent hyperbola. Okay, so people are happy. Another, so this is more general. So generally, any affine or linear function is Lipschitz. Okay. So this in higher dimensions. So d-dimensional. So if I want to write a linear function or affine function in d dimensions, how would it look like? Sorry? It would be like some theta, let's say transpose times x plus b. A would be, okay, let's do A. A would be a vector, so A transpose x, if you have seen regression, right? And then you can do the same thing, or you can take the derivative, gradient of x would be, gradient of eta x would be what? Sorry? A. So the norm of gradient of x is bounded, or definitely equal to, but definitely also bounded by this for all x. So it's Lipschitz with the value which is the norm of A. Okay, so yeah, it's a very good. Okay, sounds good? Yeah.
Sorry, can we come back to the graph of y equals x squared?
Yes.
You say that's locally Lipschitz over 0 to 1. What's our value are we going to take?
You can kind of, when I say local Lipschitz, it's a little bit more general. It means for any bounded set. So, but we can say, okay, Lipschitz over 0 to 1, what the value of L is we can take the maximum value of the derivative. Okay. In this case, we do 2, so we use Lipschitz. We can show that. So one way of it is, so okay, this is really real analysis, but let's say if you want to see why that's related to the Rademacher theorem, half of the Rademacher theorem is sort of easy. So 1/2 of Rademacher theorem. It says that, let's say it's a 1D. If eta prime of x is less than or equal to L for all x in the domain, whatever domain we have, let's say in R, then eta of x minus eta of z is bounded by L x minus z. Anyone knows like an easy way to prove this? It'll be useful for us. Can I write eta of x minus eta of z in terms of the derivative of the function? Anyone remembers the calculus fundamental theorem?
Well, limit x tends to z, eta of x minus eta of z.
Sorry, can you say it again?
When limit x tends to z,
Oh, you want to take the definition of the derivative. Let's go the other way. Let's think of the integrals. Now, I don't want to write it as a limit. I want to write it as like exact expression. Integrals, derivatives, like anti-derivatives, people remember. So tell me what this would be in terms of the derivative. Integral. So let's say x is bigger than z. X, z, eta prime, let's say t dt. Fundamental theorem of calculus. Okay. So then the absolute value would be the absolute value of this integral. And I can put the absolute value inside like an inequality. So it's like this is called the triangle inequality. I have a sum, the absolute value of the sum is less than the sum of the absolute values. Z to x, I put the integral inside. By assumption, this is always bounded by L. So this L comes out, I get Z to x dt. But this is nothing but x minus z, which is also equal to x minus z in absolute value because we assume this. Okay, this is the proof of one layer. It's called triangle or some other name, triangle inequality for integrals. Okay. Good. The other way is a very nice result in advanced mathematics that if this holds, we show that if this holds, then this holds. If this holds, then it's almost everywhere differentiable. Doesn't have to be differential everywhere. Like this absolute value or modulus, if you want. This one is not differentiable everywhere, but it's Lipschitz. Okay, so this was a side note. What I want to do is I'm going to make this assumption. Yes.
Just by curiosity, it has to be analytic, right? Versus the Lipschitz, right?
Analytic. So analytic means so analytic is like differentiable or order. So this is not necessarily analytic in that case. Right. So for example, this is not differentiable at this point. So analytic quick function would be differentiable everywhere. Right. This is a little bit different. Almost everywhere is like a measure theoretic or constant. So you could have like points of non-differentiability, but they're countable. Or measured zero. Like it's a little bit different. It's like and it doesn't have to be differentiable of all order, right? It's just the first derivative. Things would be very non-smooth in the sense that you could have like a lot of jaggedness. So something that like sawtooth, something like this is still Lipschitz, but non-differentiable, not differentiable everywhere. So, okay. So what I want to do is assume that and then control this bias. So let's do this. Assume eta is a Lipschitz. And let's control the bias. So if I do that, I get eta of x minus that integral. So it was like something like that, if you remember. And this was h, but I maybe want to do it more generally. Let's say let's do pu, du, okay. We can do it more generally. So if this is uniform and 0 to 1, this would be h, this would be 1. But I can do it more generally like that. The way to do it is that I can move this inside, or I can write it as 1 over x integral ax. Oh, actually, this is if you want to be very general, this would be nu of AX. This is really that's d nu of AX. I can write it as pxu du. This is just the probability that x. So this is really this guy. Okay. Let's not do this that way. Let's do it simpler. Might be confusing. Let's do it very simple. This was h, this was du. Okay, the simple case. So this I can write as 1 over h. So 1 over h integral of du over ax is just 1, because this is an interval of length h. So 1 over h times the integral would be 1. So I can write it as eta of x du. So eta of x is constant, comes out, right? So if I integrate eta of x, which doesn't come to du over ax, this is eta x. Averaging the constant, basically. But then they look the same, so this is going to be equal to 1 over h integral ax. I have eta of x here. That's the first term minus eta of u. Du. I have absolute value inside. I can move it outside. I can move it by the triangle inequality, similar to what we just did. Inside, I get eta x minus eta u du. Okay. Now what can I do here?
X minus
What is that?
mod of beta x minus eta u plus tan x L times x.
This is bounded by L times x minus u. So I get 1 over h, L comes out, x minus u du. Okay. And so if you remember, so a of x is an interval of length h. Oh, sorry, right, yeah, okay. The same x, this is x, good. So x is somewhere here, and u is also, we're integrating over ax, so u is also somewhere here. So the distance x minus u is at most h. So this is at most h. So I get L h, the h comes out integral ax du. But this is also, sorry, this is h. This is h as well. So that once the dust settles, this is LH. Right. You could repeat this experiment, like not the experiment, the analysis more generally, for more general nu. The same idea happens, but and then you can also do it with higher dimensions. Let's say if it was uniform on the d-dimensional cube, you go through this. This would be h to the d because that's the volume of the cube. But then when you integrate it with h to the d, this would cancel that, and this would be the norm. If you're in the cube, the norm would be still bounded by h. So yeah, so the finish of the as well. Sorry.
It will be h to the d, right? The integral.
The integral will be h to the d. This would also be h to the d because this was the size of this was really the length. Now will be the volume. So if you do it properly, these would cancel out. Basically, this would be, you don't even have to do h here because this would be like 1 over this, and then this would be integral of ax x minus z du. You bound this by, let's say, some h, And then you have the integral over ax, and this is just that volume, they cancel out. So you don't, if you do it properly, you don't even see h to the d here. This would be either in the t-dimensional case, either h or root d times h. But if you're of h, okay, it's not going to be h to the d, for example. But anyways, that's the order of the bias. Okay, so if you're Lipschitz, then the bias goes linearly to 0. Now, because I have, so is this quite clear? So if you now expand this, not expand, just put back everything together, putting everything together, I would get something like this, expectation of eta hat x minus eta of x squared, remember it was bias squared plus variance. So this is less than or equal to, I'm going to put approximation because the variance is approximate. This is sort of also a little bit approximate because there was an approximation, if you remember. You use the law of large numbers. So use law of large numbers, so it's not exact, but if you put o's, little o's, it would work. So, but approximately for large n, this would be this squared. This would be sigma squared over n h. Okay, in one dimension. So you can easily see now that when I increase h, the bias gets worse, this gets better. Right? Decrease h, this gets better, this gets worse. And if you plot it, it would be something like the bias is quadratic, right? And the other one, the variance goes down like that. And the plot would be somewhere between. So the sum would look like this. So you get these nice shape that people like that characterize the, so as a function of h, let's say the bandwidth. So we should expect this blows up, then it goes to 0, and it blows up and it goes to infinity. One because of the variance, one because of the bias, and there's some sort of optimal here choice. Okay, so this confirms. So we did it for classification, which is quite different, but you saw the same kind of behavior. This we did it for regression. For regression, it's more like comes out very naturally because you're working with the MSE and you can do this calculation. This is what it looks like asymptotically. So if you plot it, it's going to be some like wiggles around this because you're using law of large numbers. So if you in practice, it would be something like that. Okay. When n is large, approximately looks like this. And the entire thing goes, so the variance sort of scale, I'm not showing this scale, but things go down, but that's in the nature of the thing, okay? And then there's some optimal choice here that you can like try to minimize this function over h. You're ignoring the actual concept, but if you try to minimize this, you can sort of convince yourself like, yeah, take derivative set equal to 0 if you want, or you can just argue that I'm going to set these two equal. I'm going to work with h that makes the two contributions equal, because otherwise one is bigger than the other. And this is roughly the optimal thing to do. So if I do that, then you can calculate what the optimal h has to be. So you get L squared h to the third sigma squared over n. And so h would be, what would it be? Sigma squared over n L squared. Let's do L equal 1. I don't want to worry about L. So L1, then this would be just squared. So what I get is h would be, this is n. So sigma squared over n to the power 1/3. And when I plug back in, the two terms would be similar, right? So it would be like, would be less than or equal to approximately, so the first term is h squared, the second is sigma squared and h, and both would be the same, so it would be roughly 2 times h squared. Because the way I said it, let's say, okay, this is h star, if you want. So I get roughly 2 sigma squared over n to the 2/3. So with this choice, it's going to go to 0. So it's like an optimal choice. So you can see the bandwidth has to go to 0 at this rate. Like, let's say sigma squared is fixed at the rate like 1 over n to the 1/3. And if it goes like that, then both of these would go to 0 at this rate. Okay, so that's the sort of optimal rate that you can achieve for the MSA. It goes to 0, but it goes to 0 rather slower than if you know classical statistics. Let's say, for example, you did linear regression, and the function was actually linear. We get sigma squared over n. This is slower because it's like 2/3. Because we are working with a general function class. And it says, if it's Lipschitz, you don't know anything. This is what you can do. And you can actually show that you can improve this. So there are Lipschitz functions. So you can construct, for every estimator, you can find a Lipschitz function such that about this, like, at least this much. So it's an example of non-parametric rate. So it's and like goes to like if you know it's sigma, it's like going to 0, like n to the negative 2/3 is a non-parametric rate. Because we have a non-parametric estimate that we're not for, like assuming a parametric form, which we'll do next. You're not assuming that the function is linear, you're just assuming it's a Lipschitz, and Lipschitz class is very large. And so that's what we get. Sounds good. Okay, so this is bias variance decomposition. These curves are called the bias variance decomposition curves. And it's often viewed as this simple graph. This simple picture is for this kind of bandwidth estimate, or like partitioning estimator, or these Nadarya-Watsons. So the bias and the variance look like this when you get these plots. In general, it could be more complicated. But generally, you'd expect there is some trade-off. Okay. Yeah.
About the calculation of LH, like last page, like how do you go from the last step of the in green color to?
Oh, this one?
Yeah, so from this step to the next.
Right. Okay. So this is so this quantity is like x minus u. The absolute value, this is bounded by x. Because both x and u are in this ax. So that's my ax. Right, it's the sum of the partition. The u is varying in ax. Right, x is also in there. Because by definition, x is in ax. Ax is the sum of the partition that between there.
Well, just why is u AX?
Because we're integrating over. So when I put ax here, it means u ranges in this interval. Right. So you go back where this came from. There was this indicator that xi belongs to ax. This converged to this indicator that u belongs to ax. And it's just this fixed u to be in the cell. I put it down here and you can think of it as 0 if it's not in the cell, and 1 which is here. Okay, so intuitively, I'm just averaging over all the xi that are in the cell. So I'm going to only get etas that are related to those. Okay. So you're worrying about, like, the bias would be related to the things that are in that cell. Okay. So this is a pretty interesting result. There is a bit of approximation, but you can make it work. Now you understand sort of where this comes from, sort of. Questions? So I'm gonna maybe assign it as an exercise. If you do the D-dimensional case, by the hand waving argument that I did, this part would be of the same order. Maybe you would, depending on what kind of Lipschitz you are, if you're working with a like D-dimensional cube, let's say uniform D-dimensional cube, and if you believe the Lipschitz is like this, so the point is, I can change this norm as well. So this is the L2 norm, visual L2 norm. I can change it to a different norm. For example, I can change it to infinity norm. So the function could be literally straight to the L infinity norm. L infinity norm is the maximum absolute value of the deviations. L2 is just the sum of the squares. But let's say if it's if I'm on the cube, and it is like the L2. If it's L infinity, the exact thing happens that I mentioned. So let's say if this is L infinity, this still would be of this order. If it's L2, let's just split to L2 in D dimensions, then if you're on the cube, then this would be root D times H, because that's how we translate. But the thing is, the order of H doesn't change, so there's going to be a constant dependent dimension, but you get H squared. Okay, so the order of the bias is H squared is still for the Lipschitz functions. The thing that in D dimensions happen, which is interesting, is the variance gets much worse. So in the D dimensions, so let's say, okay, so D dimensions. D-dimensional cube. Let's say Lipschitz with the definition that I mentioned, what you would get is I believe something like this. You get L root D H squared. So this is H squared. There's a D, but that's like a constant there. And plus, you get sigma squared. And the problem here is that you get H to the D. And this I want you to do as an exercise for yourself. Go back to the variance and see where this H come from. Where was the H? Yeah, so this H. So up to this point, everything is fine. But in D dimensions, this is no longer going to be H. So but you do, but this is going to end up being H squared. So H to the D, sorry, H to the D. So that's the problem. So what happens is that in the D dimension, the cube is in a sense harder, so that the volume is like spread out. So you get this H to the D factor here, and so this is going to blow up much faster when H goes to 0. So imagine like if I had n times H, let's say fh was like 0.1, this would be 1 over 0.1 would be 10, right? So suppose like sigma squared over nh, set h equal to 0.1, it would be like sigma squared over n times 10. But if it's like sigma squared and h to the d, and let's say d is 10, in 10 dimensions, I would get h is 0.1, I get sigma squared and 10 to the 10. Okay, so with a bandwidth of 0.1, this is multiplied by 10, it can be killed by maybe making the sample size 10 times as big. But the same bandwidth here would be equal 10, would be like this times 10 to the 10. So I have to multiply my sample size by 10 to the 10. Okay, so this sort of captures the difficulty of estimating a general, let's say, Lipschitz function in D dimensions because of the scale of the variance. So this leads to a very dramatic drop in the rate of estimation. I believe you can like forget about the constant here, for example. You can equate the two again. And if I'm not wrong, so the optimal choice, to sort of find the optimal choice of H, and then the optimal MSE would be roughly like sigma squared over n, 2 over 2 plus d. So in d equal 1, it would be like 2/3, 2 over 3, but now it's 2 over 2 plus d. And as d goes to like get larger and larger, this gets closer to 0, and so this gets very slow. So it's like instead of n to the 2/3, you might get n to the 0.0001. So you need a lot of samples to actually like drive this error to 0. So this thing is called the like this type of rate or this behavior is called the Kelso dimensionality. So what it says is that it's hard to estimate the function in a general function in d dimensions. So for example, something which is Lipschitz, which looks sort of nice, still is pretty general. And if I just assume that, I can sort of at least need an estimator to pay this much price. So you might think, okay, I might be able to like change the estimator, I could do better, but this fundamental problem is there. The thing is that in a d-dimensional space, there's not enough points. So if you have to make h go to 0 to approximate, like to make the bias go to 0, but once it gets smaller, it's very hard for points to hit that box. Because the volume goes down very fast. The volume of like the box of length, side length. So last side length is h. So you're randomly picking the training point. Let's say this is 2-dimensional. And you see like in box 0 to 1. The probability that they land here is going to be h squared. In d dimension is going to be h to the d, and that probability is very small. So if you do it on real line, the probability to hit the interval is h. But if you do it in the square, it will be h squared. In the 3-dimensional case, it will be h to the third, and in the d-dimensional, it will be h to the d. So if this box is small enough to approximate data here properly, you need a lot of samples to keep this box enough to make the variance go down. Okay, that fundamental problem cannot be fixed. So these things are sort of the best you can do. We don't prove it here, but if your function is Lipschitz, just you know that it's Lipschitz. This, for example, is not improvable. This is some of this is like best that you can do. The alternative is to assume something more about the function. Okay, so if I assume that my function is actually linear, I don't have to pay this price. Because, for example, in d dimensions, I have p parameters. I can just try to estimate those, and I know the form of the function. I'm going to assume that parametric form, and then I'm not going to pay the scarcity dimensionality. So a lot of like machine learning or statistical learning is focused on trying to find good parametric models or good low-dimensional models that capture it's like the true function, and then you avoid this. So otherwise, you need many samples. So these are sort of these things that we talked about, like local averaging. At least, okay, local averaging is more general. So they're okay. At least this partitioning estimator that we analyze is gonna be okay in general in like low dimensions, but it's gonna start to deteriorate when the dimension gets high. And so the reason why you switch to some of these parametric models is to avoid this issue. Sounds good. Yeah, I'm gonna assign this one as more problem. It's good to go through this argument from start to finish, like the bias and variance. You get a lot of intuition. Once you do it for yourself, it's not too difficult. And you can see why, for example, different terms look the way they are, at least in the case where the data is uniform in either 0 to 1 or the square or the cube. Just assume the training data is uniform, and then these interesting sort of results that you can find rather with simple arguments. Okay, are we good? Okay, so this concludes our discussion of sort of local averaging for now. So what I'm going to do is I'm going to switch to a topic that's left over from chapter 1, and then move on to these parametric models that try to avoid this issue. Maybe So this is like switching gear a little bit, then going back to parametric model. We should really have talked about this in chapter 1, but unfortunately here, so let's talk about this. So let's go back to the idea of the measuring performance of classifiers. Any questions? Or switch? Okay, measuring performance. So we're back to classification. And one thing that we can do with classification is, if you remember, we had this loss. That's how we measured, or like, I don't know, y minus y hat. So that was our risk of a classifier. So this was Ly. And so y hat is f of x. So we took, for example, the loss to be 0, 1, but you also saw in your homework problems that you could do more general losses, y not equal y hat. That was a 0, 1 loss, then this would be the probability of error. So another way to measure the performance is to separate the performance on the zeros and the performance on the ones. And in particular, for many of these classifiers that we have, they can be written as something like we estimate the regression function and then threshold it by some threshold. So that we saw, for example, for the optimal rule is like threshold is 1/2 if this is this classification rate, but in your homework problem, you also like saw that if you change the loss, you get a different value, right? So you potentially have a different path. But the general idea that we have followed so far is that we estimate the regression function and then the threshold. So this is the plug-in rule. And this is more generally true. So you would try to construct an estimator here and then threshold it. And so the performance depends on this threshold. So you really get a family of classifiers, and you can try to report the accuracy as a function of tau. That's one way, and then you can also try to choose tau that way. But oftentimes you can characterize the performance of the entire family using this thing called the ROC. So instead of choosing actually a particular threshold, we can say what is the performance of this entire family of classifiers. And the way it's done is right, so that happened here. So what you would do is you would calculate these quantities. So instead of the accuracy, what you would do is you calculate the probability of 1 given, or y hat given 1, given y is equal to 0, and the probability that y hat is equal to 1 given that y is equal to 1. And if I had the if I know also these, then for example, given this information, I can calculate the misclassification. But the focus would be on these two. And because the classifier depends on tau, so this would be, let's say you can say this is y hat tau. So this quantity would depend on tau. And so I get two numbers. This is called, anyone knows what this is called? There are many names. I usually forget. Sorry? So this is false positive rate. So we're declaring the case to be positive. So when the true case is negative. So false positive rate. So it's a rate because the probability is between 0 and 1. It's like the fraction of, if you think of it like empirically estimated using averages, among all possible cases that are 0, what fraction we declare as 1? So this is false positive rate. And this is true positive rate. They have other names like sensitivity, specificity, which is not false positive rate. So if you look at Wikipedia article for these things, there are many different names for these, but I'm going to go with this because it's like more clear: false positive rate, true positive rate. And so this is going to be a function of tau. It's going to be a function of tau, and this ignores these class proportions. So it's nice because it discounts the base probability of classes. If I look at this classification rate, this goes in, and for example, if one of these classes is very, the probability is much smaller, that would affect the performance, the result. But this is like conditional on y, so it discounts this factor. So it's sort of nicer to work with in cases where you have unbalanced classes, because that would sort of skew the results. So if my, for example, negatives, this is very large, the positives are very small. Even if I like do very bad here, but this classification is going to be fine because this gets multiplied by that, plus this gets multiplied by that. So it's like you can calculate the error, but the errors are like modulated by these numbers. And if one of them is very large, one of them is very small, it doesn't matter what you do on the other one. So accuracy is not necessarily a good measure of overall performance. It's a measure of overall performance if you actually sample from the data, but it doesn't tell you the performance on individual classes. So this gives you a better picture. And then when you plot this, what happens is you would get, as a function of tau, you get this interesting plot usually that goes from, so 0 to 1, you plot false positive rate as a function of tau versus true positive rate as a function of tau. This is called the ROC. When you plot it as a function of tau, it does something like that. The ideal thing is like this, like perfect like that, and then the worst is like this. And so if it's above this line, it's good, and it tells you the overall behavior of this. This is a good way of measuring the performance of classifier, or like family of classifiers parameters in this. If it goes like that, it means that if I change tau to allow a little bit of false positives, then my true positive is very close to 1. So this is great. So you have to allow for a little bit of error on this. So I can always, for example, make this equal to 1, but always declaring 1. But that's not good because then this is also going to be 1. Sorry, this is I can make this 1, but by saying that classifier always outputs 1, but then this is going to be also 1, which is not good. So so this point, false positive 1 and 1, like two positives, is easy to achieve. This one is also easy to achieve because I can always declare 0. So false positive would be 0. So I want this to be small, I want this to be big. Okay. So I can make both 0, I can make both 1 equal to 2 ends. But what happens in between is interesting. If I allow myself a little bit of false positive, if I can jump to the high true positive rate, that's a good classifier. If not, then it's fine. So this can be achieved by just randomly trading. Let's say probability alpha output 1. So it's going to be alpha, it's going to be alpha. So I can trace this line, false positive alpha to positive by a randomized classifier. And so you want to do that, relevate this line, and this would be, you can plot this. The other thing that people do is they look at the area under this. It's called AUC, area under the curve of the ROC. So this curve is called the ROC, receiver operating characteristic, because it's coming from the radar, the old data radar. So whether the radar can like classify the target, like if there's something you want to like not detect it, that would be like sometimes called false alarm. You want to also good detection. So they plotted these for the radar, basically. But in any case, the area under this also is a good measure. So if you think about this, the area at the best case would be one. It would be like this. So this the optimal is one. The worst case is zero, but usually like 0.5, which is the AUC of this is the minimum. So you can always achieve 0.5. So anything above 0.5 is good.
I can have, for two curves, I can have the same area, but one is more preferred than the other two.
So that's the thing. So the curve has more information, but whether you prefer it or not, that's yeah. I not sure. So yeah, it gives you more information. So it could have like they have the same area, but depends on your application. So one could go like this, the other could go like that.
Yeah.
Right. Which one do you prefer? Is a different story, right? Depends on what you want, right? So if you, for example, can tolerate, I don't know, if you can tolerate false positive, this gives you better performance. If you can't tolerate, then probably the first one is. Right? But it gives you the full picture, whatever you want to do. If your application requires you to have a very false, low false. So you, in the statistics, usually you like this is very related to hypothesis testing. So you set your false positive rate, and then one is clearly better than the other if you have a budget for false positive. But this gives you the full picture, right? It's common people like report the AUC because it's like a single measure of performance. And it has an interpretation. So this interpretation is like the result in the measurements that they have. So if you pick two random, okay, we're actually out of time. If you pick two random points, one from the case 0, the other from case 1, this is the probability the classifier classifies like this is a score, eta hat x is higher for the positive relative to 0. So this has a 90 probability.